Hello there. Today we're going to look at Not All Memories Are Created Equal, Learning to Forget by Expiring, and the system also known as Expire-Span. It's by Sanbayar Sukhbatar, Da Ju, Spencer Poff, Stephen Roller, Arthur Slum, Jason Weston, and Angela Fun of Facebook AI Research and Loria. So in this paper, on a high level, the authors propose a modification to the transformer attention mechanism that allows these systems potentially to include much longer context spans. The way they do it is that they don't want to attend to all of the context, but in an autoregressive way, in each time step, they want to decide, is this particular time step worth remembering or not, and if so, then for how long? So after a while, these memories of the past expire and then they are dropped, and the system can learn itself which things are important to remember for the future and which ones aren't. So it has some good things, it has some limitations. It's very strong in tasks where you explicitly have to remember individual things for a long period of time. So we'll dive into the system right here. It's a pretty simple idea, I think, and it appears to work on the tasks that they produce. So yeah, as always, if you like this, don't hesitate to share this out and tell all your friends about it. I'm sure they are very, very interested. So they say, the attention mechanisms have shown promising results in sequence modeling tasks that require long-term memory, right? So they say, however, not all content in the past is equally important to remember. We propose Expire-Span, a method that learns to retain the most important information and expire the irrelevant information. They say these forgetting of memories enables transformers to scale to attend over tens of thousands of previous time steps efficiently, as not all states from the previous time steps are preserved. So again, this is the core idea right here. If you have a sequence model like a transformer, and in this case particular, we consider a sort of autoregressive decoder-only sequence model, which means that for the next token to predict, like this one right here, we only care about the past and not the future. So this is a unidirectional sort of autoregressive style decoder. So every token can attend to its past. Now, if you want to predict the fourth token right here in an attention mechanism, you have to pay attention, so to say, to three things in the past, right? If you want to predict the next token, the fifth token right here, you have to attend to this previous one, but also all the other previous ones, so to four in the past. If you want to predict, you see what's coming, right? The longer your sequence gets, the more things you need to attend to in the past, which gives us this traditional O of n squared computation and memory requirements that attention mechanisms have. So if you get to very, very long sequences, this can become a problem because you always need to attend to everything in the past. So imagine this is whatever, a sentence. The cat sat on the mat. Now, not all words, they say right here, are equally important. So, for example, it would be easy if you wanted to predict this word right here, mat. It will be pretty easy to do so, even if you don't remember that the word the is in front of here, right? The word sat here, sat on, seems pretty important because, to sit on something is a good indication that there is maybe a mat there or a chair or something like this, right? So these seem to be worth remembering, while the word the is maybe not as important. The word cat might be semi-important, And we would like a system that learns to sort of forget and remember the correct words right here. If we only remember the more important pieces of information and we discard here, in this case, this word the, then we also have one less thing to attend to. And the goal is, if we can get the number of important things down, then it won't be n squared, but it will be something like O of n times m, where m is the size of the memory that we have. This work here doesn't have an explicitly sized memory. Rather, it does the following. It goes over every element in the sequence, and every element in the sequence, of course, goes through a bunch of layers, gives you a prediction, right? So here is a prediction. I misplaced this. Let's go down a bit further here. So every element in the sequence gives you, first of all, a hidden state, right? H here, this, and it gives you a prediction, like Y. Okay, so this is H1 and Y1. Then you go to the next element, and that, with consideration, right, this layer attends to the last layer, gives you H2, and from that it predicts Y2, and so on. Let's do one more. So in this layer, so in each layer, the future attends to the past, and that gives you a prediction. And the attention is over these H right here, over these hidden state. Now, what this model does is it adds one component. In each time step, it doesn't only predict the output of this particular time step, if there even is an output, right? It also predicts this number they call E. And E is the expiration duration of that particular memory. So E is produced every time from H. And E tells you how long you should remember that particular H. So here, for example, H3 also attends to H1. I forgot to draw this in right here, right? Now, let's say that E1 here is 2, okay? Saying that this particular memory should be valid for 2 time steps. I'm not going to need it longer than 2 time steps. Now, let's say the fourth, so the next sequence tokens comes in, H4, and H4 is produced, of course, by attending to the past. But now you want to attend to H3, to H2, and because you want to attend to all of the past, you want to attend to H1. But because this H1 is already expired, you can't. So the system would drop H1. You no longer can attend to H1. So this is different from just a fixed window, right? If you have a sequence, what people previously did was something like local attention, where you say, okay, I have a window of like size L, which is 4, and if I predict this token right here, I can attend to the past 4 things. If I then predict this one, I can attend to the past 4 things. If I predict this one, I can attend to these past 4 things. So this here is different in the sense that if you have a fixed window, again, everything is the same importance, but you just limit how far you can look back. This works to an extent, but if there is something really important right here, you will forget it no matter what. However, in expire span, this thing right here can say, well, I have an expiration date of 1 million billion, right? 1 million billion. So for 1 million billion future time steps, things will be able to attend to that important piece of information. However, you can say for the next thing, well, I expire immediately. This is not worth remembering for the future, okay? So I hope you got the principle right here. They also have a drawing here where you can see these hidden states are produced, and these hidden states are produced naturally from forward propagating through the model. And for each of these hidden states, one expiration date is produced. And now in the future, when I want to produce the next hidden state, or the next output of the next layer, I can look at the past, and I only consider the things where the expiration date hasn't passed yet. So for anything else, like this one right here or this one right here, their expiration date was just too short. So this is and only these go into the attention mechanism. So this is a dynamic way of saying how long a memory should last. Now, you can immediately sort of see the weaknesses of this right here. You have to know at the beginning, like at the moment where you produce the signal, you have to know for how long it's going to be valid. And that is certainly, the case for some things that you have to remember, like when you come across a name in a story, that is maybe something that okay, I'm going to remember that piece of information very well because probably it's going to be important, but not for all, right? So sometimes something that you thought wasn't important, maybe this thing right here, you read it, it's in a sequence of text, you read that word, and it doesn't seem too important, but then all of a sudden, because this word is something, so you read on, all of a sudden that past word becomes super duper important and you shouldn't forget it. And these are effects that the system cannot handle. The system can only decide at the moment where you consume the token, how important is it, for how long should I remember it, independent of what happens in the future. You might already know a system that learns to remember things over long pieces of time, which is the long short-term memory cell, or generally recurrent neural networks that have an internal state, and then at each point they decide how to update that state. So this here is sort of an between a transformer, which you cannot decide at all how important things are and what you should remember. It's either you remember all of it or part of it, and the LSTM, on the other hand, that dynamically updates its internal memory every single time step, right? So it can make remembering something dependent even on the future. As I said, this is done for computational reasons mostly, because LSTMs you have to train one after the other. You have to backprop through time. Here, you can still get away with a bit of parallelism, I think at least. Though I would argue, if I could extend this, I would argue that if you consider the point where something expires, I would maybe build in something where the system can decide to retake this into memory, or such that the system can revise its own predictions about how important each of the memories are. And if you look at this in a, let's say, a computational point, they base their work off Transformer XL. So Transformer XL is sort of the baseline right here. What Transformer XL does is it has long sequences, and then it considers blocks of those sequences, and they do the same here. So you chunk these sequences into different blocks. Okay. Now, for each of the elements here, you output a vector, which is this hidden state. Now, what Transformer XL does is it does the attention in block 1, just as it would do regularly, and then in block 2, and then in block 3. So it chunks the sequence and handles the blocks individually. However, in block 2, in order to look back, because we always want to look back, we want to remember things, what you do is you put the hidden states that you produced in block 1, you sort of put them into like a little bit of a a register, I would say. So you put them into, so these are the vectors. I just lay them on their side, right? These are the vectors, and you put them just there. There is a sort of a stop gradient right here, but you just kind of put them to make them available for the next block. So what the next block can do when you want to predict, for example, the hidden state of this thing, it can attend to, obviously, to the sequence elements in its own block, right? Because you consider the block as a whole, but it can also attend to these things right here. And again, you produce that hidden state ultimately from it, and from it every element in that block, and those go then to be available for the next block to attend to. And you can even remember multiple blocks like this, so you can sort of carry forward this block as well, right? And now block 3 can attend to the last 2 blocks. However, you can't do this infinitely, right? Otherwise you're going to run into the same problems, but at least this handles a bit of the backprop issues. And also these things right here, they cannot attend to each other, right? There is no need for them to attend to each other. So you don't have n squared, you have n times whatever that here. So if this is m and this here is n, you have O of n times n plus m. No. Sorry. Yeah, but n is way smaller. So it's n squared, but n is way smaller. N isn't the whole sequence length. Maybe b. Let's call this b, the block size, right? And this here at maximum is n. So you have a way smaller sort of, way smaller quadratic blow up only inside the block. And you can even compress these memories here of Transformer XL. You can max pool, you can learn to compress them, and so on. So this is the system that they base off of, right? They also consider sequences in these blocks, where inside the block it's just regular attention, and then you can attend to the past as you would in Transformer XL, except that some of these past memories, they are forgotten. So here, these are maybe forgotten, and maybe this one is forgotten too, until you are here, right? And then during that time, one more expired. So you can see there is a lot less stuff around. So you get away with having a smaller memory, and you can potentially up the time that you can look back into the past. If you only have a limited set of slots available here, you can increase that. So I hope that is a bit clear how they do it. They go block by block, and in each block they look back, and they build this memory right here. So this memory here, that inside the next block they can also attend to. But in the memory, other than Transformer XL, they only consider things that have not expired yet. And the expiration is determined at the moment where the signal, where the hidden state is produced. Right? In fact, the expiration here is pretty simple. So you take that hidden state that's produced by the network, and you simply perform a logistic regression on top of it. So the logistic regression here will give you something in the range 0 to 1, and you multiply that by L. And L is the maximum possible length of remembering. Right? Now, these are all, design choices. You know that the sigmoid function here used in logistic regression is a rather, let's say, rather steep function. So there is a region where you sort of go up quite quickly, but there are also large regions where it's just all or nothing, right? So I'm going to guess that this function here will be either remember this or don't remember this. Maybe there will be some in the middle, but which tells me that this L setting right here might be fairly important, that you tune that for the task that you want to consider. Another thing they say is, okay, how do we actually implement this? And they implement this via a mask. Okay, like if you have a bunch of things that you could attend to, right? The way that you don't attend to everything is by masking out attention parameters, essentially, or elements of that map. So if I draw the same sequence twice, the attention matrix is, of course, constructed by outer product of keys and queries, right? So here is the attention matrix. Every cell gets a value of how much this X here attends to this Y. And as you know, that already in these decoder things, we need a mask because this thing here cannot attend to this thing here. This thing here would be like this thing here, so it cannot attend. So all the upper triangular thing right here is already dark. Well, okay, I can't draw, but we usually implement this with a mask, right? Because GPUs aren't super good at doing triagonal matrices. So we just put a mask here and we say everything up here is off limits. Okay. Now, if we also say, well, let's say this thing here has an expiration date of 2, which means that this can still attend to it, this can still attend to it, but this here cannot attend to it. So what we need to do is, well, I might have drawn this slightly weird, but let's say that is this. Nah, it's not correct, but you go to that cell and you also mask that out. You say you cannot attend to anything that's expired. So what you end up with is sort of this mask where you fill in, I think after that it should all be black, right? Where at some point the row will just be masked out from then on. So the light squares here have a value of 1 and the dark squares a value of 0, meaning that you don't consider these things in the attention anymore. That's how it's implemented. If you just do that, then you have a problem on your hand, okay? Because this is not differentiable. Simply putting the masking, whether or not this R number, R is the thing still valid? You see it's constructed from E, which is the expiration duration, and the T, which is the current time step, and the I, which is the I from the E. So you look back and say, is this thing still valid? And this number, if it's positive, it's still valid. If it's negative, it's no longer valid. If this becomes negative, it indicates the memory is expired and can be removed from the set you attend to. So you construct a mask with just everything, all the R's that are positive, and use that mask in the attention like you already do with the masking out future tokens. This is not differentiable, okay? However, they say with such discrete masking, the expire span will not receive any gradient for training. Instead, we use a soft masking function that smoothly transitions from 0 to 1. And this is what you can see right here. So essentially how this works is, here is a memory, produces a hidden state, and it says, I am valid for 3 steps. 3 steps. So that means that the mask here, how does the mask look? The mask for this particular thing looks as follows. So here is 0, and here is 1. The mask, okay, well, yeah, the mask starts at 1 for 1, 2, 3, and then it drops off linearly until it's at 0. You can see this right here. So here's the min of 1, which means that it can never be higher than 1, the max of 0, which means that it cannot be lower than 0. And then in between, it's governed by this rule right here, which you can see R is a hyperparameter saying that a ramp drop-off. The length of a ramp that is bounded between 0 and 1. And the higher this R is, if it's negative, then we're in this decreasing regime. Okay, so this is the mask. Now, you can also immediately see that talking about gradients, right? The only place where the module that generates E, right? This is we generate this here, the hidden state goes into a neural network, and that generates this expiration date. The only place where that neural network gets a learning signal, gets a gradient, is during this drop-off. No, not before, not after. The only time where this network gets any learning signal at all is during this thing. So it is quite important, these parameters, right? This here, this is upper bounded by the parameter L. And then this thing right here is modulated by the parameter R. So these hyperparameters, I feel, are quite important to how this task is going to play out if you actually want to learn anything. Because let's say in a sequence, here is something that you need to remember, but you need to remember it for here. If the L is too short, right, you will maximally remember it till here, and then it's gone. Even if the L is large enough, right, then you won't get any training signal for this unless sort of let's say the L is large enough, so this is your expiring span, and then it sort of drops off, the importance drops off, and only if that drop-off happens to coincide with the thing where it's important, you do get a learning signal that, hey, maybe you should remember that thing for longer next time because I'm going to need it, right? If that is not the case, if your expiration prediction is like this and your drop-off is done here, then you will never get a learning signal that, hey, there might be something here where you should remember this thing. This is, it's the same problem you get anywhere where you're dealing with long sequences. And it is a problem because ultimately, if you want to have a general training method where anywhere in the future there could be something important, you're going to have sort of this quadratic thing where you technically have to attend to all the things in the past, even a little bit, because you want to make it differentiable, because you want to learn to remember, right? If you always forget, and then there is something here, you don't know anymore that there was something to remember. You somehow need a learning signal. I guess you could break this, maybe you could break this down into maybe not n squared, but maybe like n log n, where you sort of build up a tree of the past, and then you somehow realize that, okay, there is something to remember. You don't know what, but maybe there is something to remember. This might have been done already. In any case, I just wanted to show you that the learning signal here is very small. Like the window where you can learn something is very small. And that means the kind of tasks it can be applied to are maybe not as many as you would hope. What they also do is they put an L1 penalty, so an L1 penalty onto these expiration things. So they encourage the network to rather forget things. This is in order to keep just the predictions small. You don't want the network by default to say, well, none of this is important. And only if you get a learning signal that something is important, then the network should predict high numbers. So ultimately, you're going to have a sequence, right? I'm going to draw it like this time. And the network will predict various spans to expire these memories. And the first thing you do is you'll say, okay, everyone just kind of go down, go down, go down, go down. And then if, let's say, this thing right here really profits from this thing right here in the sequence, then, and if this has been going down enough such that the later one is in this ramp portion, this R portion of the former one, then you get a learning signal saying, hey, maybe you should remember that thing for longer, right? And then hopefully some next thing right here will also benefit from remembering this thing. And now that is in this in this ramp region, which will give here another boost to remember it for longer. So this is how you learn. You sort of need a continuous reinforcing signal over different time steps in order to learn. This long range thing, it's I don't think that generally is learnable with this system. You need these intermediate things, or you need some kind of randomness to discover it. And this is very close, right, to reinforcement learning now. All right, and so that's what they do here. They have some practical considerations where they say, okay, because we cache these things, like the question is, how do you even backpropagate through something like this? I said there was a stop gradient right here. What you do is you cache the H, you cache these things, and then as far as I understand, you do compute the attention, like the expiration things on the fly. Like you cache the hidden states, and then you compute should you mask them or not, you compute that thing on the fly. And so you can backpropagate to these variables even in the future, because you have the H's cached. I don't think the backprop flows back to when the hidden states were produced, because, well, it can't, right? Because you cache it. You don't have the graph available anymore. So they have a bunch of practical considerations right here, and now they test this. So they test this in various tasks. For example, there are these reinforcement learning tasks. There are these text instruction tasks. There is character level language modeling, collision detection, where you have a video, you go frame by frame. So these tasks, I guess, except the language modeling tasks, are quite constructed such that you have to remember long things. Particularly interesting, for example, is this one right here, where they do have this character level language model, and then they look at what does it learn to remember. And you can see right here, if the sentence is powerful influence in Egypt, right? And they say this, the model strongly memorizes the two areas, Egypt and Alexander. So if you look Egypt right here, and this is the visualization of the expiration time, this is strongly remembered. If you replace, in the same model, you just replace this with the word somewhere, all of a sudden, the model doesn't remember it anymore. And if you replace it with Humpty Dumpty, again, the model remembers it quite well. So this is an indication that the model has in fact learned that, if there is something special, and they claim if it's a name or something like this, the model remembers it well. They also say the rare words remembers those in memory. And I'm asking myself, is this just a function of, let's say, perplexity? Like, could you just remember the things where the model perplexity is pretty high instead of learning what to remember? All right, so you just remember sort of the things that you would not have predicted. I'm going to guess the learned remembering is better just because it's learned. So it can also remember things that have a low, like that have a big probability but might still be important. I want to talk just a little bit about this first task right here to show you the kind of tasks where this could be good at. So here you have a grid world reinforcement learning approach, and you're at the start. You are able to observe the colors of the fields you're on, right? So you're at this start right here, and this is either blue or red. And then what you need to do is you need to walk all the way through this long corridor, and then you need to go to the correct door. And the correct door is whichever one was, the color was at the beginning. And the long corridor is made such that it is too long to be in the same block, right? It's too long to consider in one attention operation at the same time. And this model, they say, it learns to remember the correct thing with very little effort. So here you can see the comparison to Transformer XL. So Transformer XL also has the ability to remember that, right? It can simply attend to this thing in the past if given enough memory. So here you have the memory size, and you can see it starts out by being just kind of random because it doesn't remember. The memory size is too small to actually remember. And as you give it more and more memory, it learns to attend to the correct thing in that memory. However, expire span, it doesn't have a set memory, right? You can, with the L1 penalty, you can sort of modulate how long it forgets things. But these here are just 5 random samples, I guess, of the same model. And you can see that it solves the task pretty well, while its effective memory size, if you calculate, if you look at, what things you do remember, stays relatively low. So it learns to remember this correct thing right here, which is pretty cool, right? However, there's details of how this task was constructed. I already said if it's just a long thing, then this is if this was just a long corridor, this was unlearnable. So if you look at the details here in the appendix, where is it? Yeah, the corridor task. The corridor length is sampled from between 3 and 200, right? So, and for the expire span, we set the maximum span to 200, so it's able to remember, which, again, this L seems to be an important hyperparameter, and the ramp length to 16. So what does this mean, right? If you have let's say I don't even know how many things they consider at the moment, what's their block length. I'm sure that's stated somewhere. Okay, but in this corridor task, in a reinforcement learning problem, right? If you sample things that are just 200 apart, right? I guess you can learn because your L is 200, right? But your predictions, if they are too short, then you never learn to get up there. And if they're too long, okay, you have the L1 penalty, which makes them shorter and shorter and shorter, and eventually you come into the field of learning. But here you sample at random, so sometimes it's 3, and sometimes it's 200, and sometimes it's here, and sometimes it's here. So you give the model a really nice training signal wherever it currently has learned, for however long it currently has learned to remember things, there's going to be this ramp, and there's going to be some training runs where the length of the corridor exactly falls into this ramp, and that will give it a training signal saying, hey, you maybe should remember that thing for longer. Okay, for longer, then the ramp is here, and then there will be some kind of problem that exactly falls into this ramp, right? So as in reinforcement learning, it is best, I'm going to argue, if your loss structure guides the model to remember things for longer. Of course, this doesn't work in the character level modeling, but there I think the text is naturally structured such that if it's something important to remember, you will find instances where that comes after 10 tokens, and you will find instances where the need to remember comes after 20 and 50 and 100 and so on. So yeah, not for every task, but certainly for many tasks, this might be a good solution. Again, I would advocate to add the ability of the model to refresh these memories, not full LSTM style, so not internally compute and update an internal state or something, but just to go there and say, well, in the light of this new evidence, this thing right here that I wanted to forget now, it might still be quite important, right? So that would be my first extension. And my second extension would be, instead of building some sort of a bank right here that you can attend to, maybe you build some sort of a tree, like some kind of a Merkle tree-ish thing, but not with hashes, but with hidden latent variables. I'm sure maybe this has already been done. Okay, that was my 2 cents to this paper. I think it's a pretty cool paper. If you have problems that have super long sequences and you have a clear structure where it's important to remember key pieces of information, a few key pieces of information over long distances, and if those distances are somehow distributed a bit such that it's not only super long distances, this might work wonders. So tell me what you think in the comments, and that was it for me. Bye-bye.